get started. Andras Kabai is the first speaker after lunch. As we announced, he will carry on with the workshop before the lunch, moving on with the buffer overflow subject. Andras is going to present what happens when life isn't as simple as before lunch, but let's say some defense mechanism is switched on in the runtime environment. Let me hand the floor to Andras Kabai. Hi, everybody. Heartily welcome to the ASLR and DEP bypass techniques. I'm Andras Kabai. I'm working for PTA CERT Hungary as an IT security expert. I think this is quite enough for you to know about me. For the time being, my presentation comes in two parts. I'll quickly move through the slides and then carry on with the practical demo. The previous buffer overflow is different from this, so you will really have to pay attention to this. So DEP, Data Execution Prevention, and ASLR, Address Space Layout Randomization. So, as a matter of fact, these are the techniques that can make the intruder's job difficult if he wants to use a buffer overflow exploit. In the past, in the case of buffer overflow vulnerabilities, you would just fill up the available memory, you would cram executable code into it, and somehow the EIP control should be overtaken by a shell code, and then you've taken over for purposes of running your own code. Payload runtime. With the introduction of DEP, you might say that this was made difficult. DEP was first tried in Windows XP SP2 and Windows 2003 Server SP1 in the Windows environment. So we can actually divide DEP into two parts: software emulation, which isn't really DEP, it's just called that, and there's hardware DEP. Depending on vendor, it's page address extension NX or XDBit. And with this tip over, certain memory parts will be defined as executable or not. And DEP has many switches or parameters that can be set: opt-in, opt-out, always on, always off, namely. And it depends on the operating system and service pack. What's the default setting in the opt-in case? The basic modules of the system and system files are protected, and anything else can also be invaded as required by DEP. Opt-in means the opposite. If we want an exception because the application is not DEP compatible, we can define an exception rule. Always on means that DEP restriction will always be valid, and always off just means disabled full time. And the biggest cut with DEP is that the earlier overflow exploits are not working, or basically not working, because we got used to the idea that there's a buffer which we fill up with all kinds of nice code, including the payoff. And typically, after the exploit, the register or a stack pointer or some other pointer or register would actually point to a nice buffer, and the EIP is controlled so that it jumps to a specific memory address. Or we can use a call to, and the code will run. Well, this is no more from this point on. ASLR. typically Windows Vista and later Windows releases are using these, and in 32-bit systems this is quite a poor solution because the addresses are stored in 4 bytes, and randomization with the top 2 bytes means 16-bit memory addressing, and also the memory is further reduced by 64-bit addressing, and the modules will be restricted in 64 bits. Obviously, you have an order of magnitude more memory addressing, so obviously ASLR occurs above 64 bits and as of 64 bits, and the essence of the operation of this is when an ASLR program or module is uploaded to pull in the DLLs, for instance, they move into a variable memory range. So we can be sure that in one moment or after booting a certain function is accessible at a certain address. The next time you boot the computer or change the status, the same address may not give you access. And obviously there must be a way to manage these addresses. And the function calls must be manageable. There are procedures when the application initializes itself. It calls in a table of functions to be used later, but an intruder cannot have access to that, unfortunately. So in the course of the overflow, you won't immediately find out the location of addresses. And in addition to ASLR, changing the basic addresses heap, stack, and BEB and DEP will be randomized. So this makes your job even more difficult in certain cases. And here's a big cross mark because the earlier overflow exploit utilizations got the payload in, and we said that a Windows exec could come at a certain address, and only the address of the function should be at the operating system and patch level. Depending on the language, it had to be selected, and we got an exploit that was fully operational throughout the Windows range. And from this point forward, this simply isn't working. So it's no use to know that this key function kernel would be located in this exact place within kernel 32 DLL, but the base address could be essentially different, and it will be different. And yet, there are ways to bypass these. And let's see what the process is. A DEP bypass is what we are talking about, but it's important to know that we are not talking about bypassing the hardware DEP. So this is not a hardware DEP shortcoming. It's an operating system and software implementation loophole, basically. Certain features are not coordinated, and that's how we can get into a protected memory area that is protected by a DEP. And for some purposes and in some ways, we can get it to run our payload code. And the most trivial solution is if we override the IP register to point to a certain address that has existing code, which would switch to DEP for the process. So you set the register content, and then you call a given function referring to the process, which would switch off the DEP restrictions. And since the function returns and it switches off the exploited memory section and lets us run our DEP exploit without any problems. Bad memory mappings. What is the meaning of this? DEP in certain cases, if coding is improper, cannot do anything about that. There are snippets of code and memory segments, and they can all be queried. And in the initialization phase, the access settings take place, and you can set it to read, write, or executable. And if you have a memory segment that is both readable, writable, and executable, then there is no hindrance to our copying our own code and to handing over the control over the EIP. And since the flag is set to executable, a DEP has already lost its power and cannot ward off the attack. Then return to libc or ROP is the other interesting process, which we'll get to know more in the demo phase. What we are talking about here is that we're manipulating the stack in a way that while the program is running, the return values read from the stack, we should get to memory addresses where we have a series of instructions that we want executed. So I save a pointer in the stack which sets the AL register to 1, and then RET will read the next value out of the stack which I'm controlling, and from then on I will send it to a memory range, which is this is part of an already implemented program. So this will bring us back to a directory with existing code sections, and these small code pieces will be compiled into what we want executed. Return to libc or ROP processes typically rely on a set of functions, and we tweak one of those functions, because even though we reach into the stack, we don't run codes, we use the return values. And we read the return values so that the program itself switches over to earlier runtime paths. So virtual protect process is one example we can call, which will immediately switch off the restrictions to the process. And once we're done with this, in the buffer level code, we can directly run our process, and we have a number of functions at our disposal. So this isn't the end of the opportunities, and there are more alternatives, options we can use if we did not know the address of any of these, because we must provide references, otherwise we can't call them. We have all kinds of other tricks to use. So it's possible to get hold of pointers, because if we know that our program around the overflow makes reference to one of the DLL functions, but a different function, then we have the virtual protect mechanism, for instance, that's of relevance for us. And if we upload into the register a value or manipulate the ELX register, we load the value without the offset, and return values will increase by 10 the AAX value, and it will always return, and we keep this up so that with the offset value the EAS register would always grow. So jump to EAX would be the command to execute at the end of the day. Heaps play. Have you heard? Heaps pray, that is, have you heard of this? It's basically a heap allocation process. So a sufficiently large heap allocation would make sure that for the address area, the address space that you have reserved, the data cannot always be found in a given memory range. So there may be randomization for the heap. There's 2 megabytes for the addressing space, and the heap can move around, but if I store 100 megabytes worth of data, I take a large knobstead and add my shellcode at the end, and this huge chunk of data will be layered and I define an array with a larger number of elements. And I keep increasing this until it almost fills up the available space, because afterwards randomization will not make any sense anymore, because the content fills up the available space. And if you stab into any portion of the memory, you will always find the same thing, or due to no thread, you get down to the shell code and get it run. So it's the job done. And Java heap spray works because Java virtual machine, the implementation to heap allocation is as follows. In the course of the allocation, heap read, write, and executable flags are handed out. So despite the fact that this is a data field and read-write would be sufficient, executable is also used.
And it points at the appropriate memory address, and then DEP doesn't do anything. ASLR. We can also do it in different way. We can bypass it in different way. One is the partial EIP override. Since randomization is on the top 16 bits, if a DLL is loaded 1122 memory addresses, if a function is found at hex address 112233, then the upper 16 bits are randomized, 3344, and the lower 2 bytes will again change. They remain 3344, 3344. If 1B is partially overwritten, only the lower 2 bytes, then we can achieve the upper 2 bytes of DLL. Will keep its actual status, and the offset will be unchanged. So with this, this is a relative space, and then we can bypass ASLR. Because of the architecture implementation memory, data traffic between memory and registers is watched, and the lower second bytes are overwritten, and if 2 more bytes are added, then third and fourth bytes are overwritten again. This is how we operate. We also have the opportunity to use non-ASLR modules, where function addresses are fixed, load address is fixed, base address is fixed, base address always fixed, and the offset is permanent. Nowadays, more and more programs are translated, interpreted in such a way that even big vendors produce modules that are not ASLR capable. If we look into a DBOO environments, then from the loader program we can say which modules are non-ASLR and which are the ASLRs. Because we can use static addresses which are always there, and even if we use injected code into a random place in a memory, if we can make references to fixed addresses, because all the codes are there. Brute force. It is possible to use brute force to find the DLLs in these addresses, especially for 32-bit systems, because of the poor randomization and the smallness of the labels. So if we run into such an exploits where which can be utilized without stopping the program or putting obstacles into the running of the program, then we can scale down the address space, and then we will find the given function within the space. Memory information leaks. Very easily we can gather information from memory leaks. I already mentioned this. It is imaginable that within the given DLL, a non-relevant function is called by the given program, and we know where it is called. So we know its relative space, the relative address within the program. And whenever we are running our own code, then we have the opportunity to rewrite this pointer and also save our pointer into our register. And with the offset, we can really call the function desired. Heap spray procedure is the same. The only difference is that we use JavaScript. And with the use of JavaScript, we cannot directly have a runnable memory system, but because of the large amount of heap allocation, actually the essence will evaporate, and offsets are capable of giving relative locations, even if we do not exactly hit the beginning of our payload. And then the application uses the offsets to recalculate the entry point. Simply, it steps the program forward till it finds to the payload, valuable payload. And what if we have to bypass ASLR and DEP together? There is a solid defense, but the two together can make the situation of the attacker difficult. We need at least one non-ASLR module in the loaded exploited environment. This is about 99% of all cases. If we find such a thing, then we can build on it with fixed addresses. With the offsets we can reach modules and functions with which we can bypass DEP, and we are ready. Find a pointer and use an offset. Type of attack is again looking for a function within the given DLL with a certain offset, and we can reach the function with heap spray, and ROP is useful. ROP is a return-oriented programming technology. Return to whatever. It's not only for live C, but anything can be used in relation to what we can access, how ROP operates. We have a stack, as always, and somehow we produce an overflow in the stack, and we control the overflow. ESP points to the top of the stack. This is what we want to achieve. It can be ESP or something set during overflow. A part of segments that jumps to ESP or any other similar solution. As soon as the ESP points to the top of stack, this part is considered as an array of return addresses. We look for code parts which we can put together step by step, and then we can get the payload what we are looking for. If we have a 100-byte payload, then with certain assembly instructions, we cannot put them together with simple assembly instructions because there are small fragments of codes on which we have to rely, but with some tricks. For example, if you would like to increase the value of a given register by 100, then it is not quite sure that we can find such a code. We may find a place where it increases its value only by 50, and then we call it twice, and then we have the same result. So always we have to do tricks, but sooner or later we can get the ESP. If there are these two values with which I would like to load this, then we have 4-byte value here, 4-byte addressing 4-byte value here. This address points to a code segment where we have an EAX and ret. Since the stack pointer points to this code section, and we use a ret to get back, ret will read out the return address, and pop EX runs using the value in the next address, which will be put into the hexa 4141, so letter AA, and then it returns. But with this readout, stack pointer points one down, and then we have the pop EBX address, and then the value here. With this ret, we will jump pop EBX, and then again we jump one down along the stack, and so on and so forth. This will be the new content of EBX. And then the next code section is read, and then we can build up the payload instruction by instruction. It's not easy to put a payload together to find these code segments, but it is a real serious thing to find all these elements. But there is something which can make our task easier. This is the PVE find address command, PI command for immunity debugger, actually put together by Corley boys with lots of useful functions within the debugger. We can look for modules like NOAS, which modules do not have safe SLRs, SEHs. We can also mix these parts, and the important thing is ROP and ROP call. And also there are modules that are not protected by ASLR. This is what we can use in an ROP instruction. So it looks down the line, checks all the accessible parts, checks all the rets, and then builds up a couple of instructions, looks back a couple of instructions, and if there is anything usable there, then it is collected from there and put together in a big list with a label. And then we have got to the point of the ROP demo. Let's see how we can use this technology in real life in demonstration. XP, SP3 are used. And what is the most important thing here is DEP always on for each and every process. We have an audio converter, of which we know that it has an accessible exploit, although I couldn't get this exploit, but we will totally rewrite it. Like this. From the back, can you see it from the back? Because from the very back, nothing is visible. Is it readable? Shall I magnify it? So we are going to generate a paylist file. In order to specify the buffer positions, we should save certain addresses in the exploit. This is a unique pattern that we generate. Probably you have seen it. This is the Metasploit Workshops product, 15 bytes pattern. There is nothing extra. We put the whole thing into one file. We have this playlist file. It's a stupid program. There is no control, no format control. Now let's see what it will result in. We have an immunity debugger with which we can link the whole converter. Let it run. And that's where we open the first file. All of a sudden we have access. And then if we take a look, then it is immediately visible that this is the pattern. So in real fact the register should point at it. But if we use an override to point at this point, then it will just kill us right away. But if we just move down the line, then we find something interesting in terms of offset. So in this situation, we move on like this with a simple pattern set to ask about the given sequence of numbers and values, and then we will receive the offset where we can override the structured error handler. This was the address that you should remember well, 4000 something. I can't see it from here. And then using this we take a step further. 4436 was the offset from a base address of 15,000. We fill it with the letter A, and then we put in the address of the SEH record, hexa 4242 letter B. 41 is A, 42 is B, and then we will just fill in, dynamically sizing the rest of the bytes. If everything runs smoothly, and if we open our second playlist file, then it will be a structured exception handler, which should be overwritten by, at the address of our selection. Can you see this? We can control the running of our program by means of the SEH convert file from this point on. If we go back to the window here, then again we can see that our stack pointer points into the big nothingness, into the wilderness, and as we go down, all of a sudden we can find the letters AAA, and this is the point where we should jump. And then we use the first step of the ROP method, where we would like to find a code section where the value of the stack pointer is increased by something, and there is a ret afterwards. We have an ROP file, pvf fint address tool generates this. The reason why I didn't generate it right here is because it may take several tens of minutes. It's a small module, and for bigger modules it may take days or hours. And we have megabyte files. We have nothing else to do but search in this file for what? We need a path where we have add esp, something exists. There are lots of similar instructions, but on the battlefield we must shift a 3-digit hexa number, so we filter a little.
Ha minden jól megy,
And if everything runs smoothly, then we will get those values where at least 3 numbers or character values can be found. And we may select any one of them, non-ASL modules, ASLR modules. So we may freely choose. This is a non-ASLR module. After 1.5 days of debugging, I understood that it won't run because I couldn't clash with any restriction in the virtual, even if the virtual system enables us, it wouldn't limit us in our efforts. So we take out something from here, and then we use this. And since it is accessible at a fixed address, we can simply jump at it. And then this is a structured exception SE, and we need the address in the reverse order of the bytes. As I mentioned, this is the order needed in the registers. And then the SCH record is overwritten with this value, and then we check what comes out of it. Mindjárt végre lesz ennek, kicsit addig csinálom. So let's check what the result is. Access violation arrives after loading, and probably we got to the right place. We put a breakpoint here and let it run on. And then we also use the breakpoint. And then there is the SCH override, and this is the number, which points to or ESP points to this point, and then we move one down in the stack, so we are at the right place. And then we can see that we jumped into the buffer space controlled by us. So we won't play with it to use to find the exact entry point of our buffer. It's enough if we go down to this point into the middle, and then the offset and the addresses are calculated from here. There is a little difference between EDP and ESP, and if we take a look, we can see that we must go down, but we will sooner or later get to the starting point of our buffer. For this we need an instruction or command where we can use EAX. It's a bit quick, but probably you can follow him. And then we are looking for a move, if I can see it correctly, command. There are lots of such commands, but we can select any one of them deliberately like this. So one content of one register is filled into the other register, and then there is a pop command on the stack, so it pops out something from the stack. So we must push down something in this place. The important thing is that the running of the program shouldn't be interrupted. In fact, we should use this one because there is only one pop behind. We load it, we read out one value and return to stack. And if we implement this in our code, then this is what this is the memory address, the given memory address, where there is this sequence of instructions, SCH instructions, if I'm correct. And if we just take a look at the time of running, then we can see that when it is executed, EIP runs to this address and it saves it into the EAX register, and the next buffer value is filled with hex IAs, the code 41. I hope you could follow him. It's really beating everybody. Breakpoint, SCH change. We have ESP manipulation. That is, we found it. Unfortunately, moved in the wrong place. We positioned into a wrong address. So we have to rework or re-edit it a bit. So actually it was a miscalculation on my part. We should put a smaller distance between the two places.
Szintén.
Here again.
Hopp. Így is van. És
that's it. And that's where we wanted to jump to the desired part of code. So filling the register, then we pop out a sequence of bytes from the stack. And these are the letter A's 41, hex 41. And since the next function is not written, it cannot jump to the address 41, 41, 41, 41. So from this point on, we can see that how we can put parts of programs under one another, and then payload is generated. And we should decide our target. Our objective or target should be the calling of a Windows function. And we should try to run a command, what he said. And this is our target, our aim, our goal, our objective of the loaded modules. We select or we check kernel 32 in its appropriate space, the export of something, which has an address, and then a WinAccess function is really called, but certain parameters must be passed beforehand. Loaded modules, outcome DLL. We check the namespace part and we say kernel 32. From kernel 32 it imports the wanted command, which points to an address within kernel 32. We check the difference between them. We cannot get access to WinAccess, but then we access the address of the file, which is initialized in normal loading, and the write file function and the WinAccess, the offset between the two is used to call WinAccess. Our program is running. This is the memory address of WinAccess. This is what we want to call. We put it into the buffer. And WinAccess needs two parameters, one pointer to the command to be run, which is a string closed with a byte 0, and then must show to a byte value, which is the setting of a window. Decimal 10 will be displayed on the basis of default settings. This is 6. Exploits number 6. If we open it, we play the normal steps, structure and a breakpoint and so on. We make it run. We have a first ROP command, adjustment of stack, and this is ret, but ret is not written yet. Later on here it is in stack, kernel 32, C reference, and behind it this is the X path, which is the pointer, and this is the setting of the appearing window. In the stack we must place a string calcexa with calcexa, and we should increase register EAX content till it points to this address, and then we should find a part of code which loads the value of EAX register into the stack, and this address should be here. And if it's done, then we can take steps in the stack till at the return point, at the return command, it moves us back directly to this address. That's what we would like to make.
De lehet, hogy egy kicsit begyorsítok, ha jól látom, 12.
Well, I'll speed up because we've only got 12 minutes to go. Or how much?
Szóval a EAX registert kellene valahogy...
So the EAX register should be increased somehow with a beautiful value, let's say 100, added to it. And we have this address to achieve it. If we jump to this address, the EAX register value can be enhanced by 100, and then in the EPP there will be a value that we read and the stack will be adjusted to it, and then we return. We do this several times until the EAX register reaches the appropriate position and points into one of our buffers. So coding this will make this the second ROP instruction. And let us just note that we're translating addresses into bytes after the EAX saving process will add 100 to the value, and the EBP will be read from the stack, and 4 bytes will be added after the function call, which the pop EBP is going to read. Let me move on. We'll not look at this in this one step, because we know that it has to be executed several times. So one red is going to read this value out of the stack, and then it will jump to add 100 to the EAX register and then read the EBP value, which is this, and then at the next return address, which will be the same address here. So again, the EAX register will be added 100 to it, and then we return, and this goes on and on like this until this point, when the EAX register is in the appropriate position, and we define a string car.exe, and we also end a 0 point to the end, and all of this is packed into the kernel 32.winexec file. 16 bytes of space holder, after which the commands will be added. Let's see what this looks like in real life, this number 8 exploit. Access violation took place. Now we'll check the breakpoints, stack modification, And if we check this, we jump back to the previous address where the AEX register saves the EBP, and we return to read the add AEX 100 code snippet value. So the next step will get me to this address. AEX will be added 100. We read the EBP, and hex 41 has been loaded into it, and the EBP is the right value, and then we return, we get the next return value, and again AEX is enhanced, and we run this a couple of times. Again we come back. Let's see, ESP is now pointing to the letters A. AEX is not in the appropriate place yet, but if we add another 100, then it is already pointing to CalExe. A pop EBP, another read, and we return, which is causing an access violation, so we have not continued yet, but it's time to move on. The AEX register is pointing to the right place, and we need a pointer. AEX should be saved into the stack before WinAccess calls, because when the call takes place, the values are read, and it will point to the string that must be run, and it will become part of the Windows settings. So somehow we need to save the value into stack. We look for a command that goes into the stack segment to the area where the ESP is pointing, because ESP override doesn't make sense, but it's like shooting ourselves in the foot. So ESP and then EAX should be written. Yes. Eword Peter, 4 bytes should be written. And we have these, but it says C, C plus C plus C plus 8 EAX. Write only at the ESP plus 8 address. That's insufficient, actually, because we can get 8 bytes below ESP to write, and then we could return to the next return value, and directly WinAccess should be called at that point, but WinExec will look for parameters at the address plus 4 bytes. So this isn't going to work. We must use a trick. We're causing another crash at some other point. If it ran. Well, we'll find ESP plus 10, and that's sufficient space so that we can save our pointer to the appropriate place, and then we can do lots of things before we call the function. We have many function calls, but none of them are appropriate until we've found something like this. If you look in the stack after saving, there's immediately a call, which we did before, but those calls jumped to wired in places. But in this case, the EBP pointed address will be the target of the jump, and that could be good. So EDI should be set somewhere, either through a register operation or defining a value. Or we should find a code snippet that goes pop EDI and return. So it should read the EDI value out of the stack. We'll find one of these, and then noting these two addresses, pop EDI, and the stack saved value can be used so that this becomes a useful piece of data. So let's see how we go about this. The EAX register has been set, and the earlier operations took place. So now we have a pointer in place in the form of EAX, and pop EDI has been introduced. Pop EDI is returning out of the stack of value that is only known to us. It's full of X's. And then call ED, which would crash, because obviously lots of X's don't represent an executable memory section, but we need to analyze the runtime environment so that we know about the address and the executable snippets running this. Then after the usual steps, breakpoint, stack change, EAX, register positioning, and we've reached the new command, and that's full of X's, hex 58s, and with return we got pop ED, which also looks up the 4 bytes afterwards. It's full of 58s, and with the next return we're saving into stack. So the pointer value of EAX is pushed down into the stack, and then we get EDI, which currently cannot be interpreted. Calc exe can be saved here. As you can see, it's a bit higher up than winexec, the call we made, and the area we set aside for that, but no problem. This placeholder area is reduced by the appropriate number of words, bytes, and winexec is going to make the call here, and then the parameters to calcexe, and that's pointer to the string, and if we restructure that, it can work, and the stack pointers must be moving on so that they get as far as the WinAccess call. With a small trick, as you can see, after calling ED, we still have free space, a few bytes, which we'll have to leap over. We've done two things. First of all, kernel 32, DLL, and WinAccess instructions were brought forward. So we reduced the front part, and the back end is enhanced. So EAX is going to point here, which means it will save ESP plus 10 to this place, the appropriate place. That's the place for the EAX register under the program. And then we'll call EDI, because we're still a few bytes above the desired area, and what we do is we add 4 to the register, and kernel 32 is going to get the return value. Let's see what the end result is. We'll load it in. Let's see the chef change, and we do a breakpoint, and then a stack point change EB, the EBP saved, EAX positioned, EAX pointing where it should, and then EDI setting an internal audio converter addresses where it's pointing. That's where the stack pointer will be fixed. We return to the following address. We save the EAX register, kernel 32, and the call underneath is in the appropriate place, cal exe pointer is pointing there, we call on EDI, which adds 4 to the stack pointer, nothing else. We return, and since we're 4 bytes higher than we should be, again, we do this again, and WinExec is going to be the next call with the appropriate parameters, which means that even though we were in an area defended by a DEP, and we did not run a code in the defended, in the protected part, and yet we could have anything executed, any command done. You could add a system, or you could enhance the operation as you wish, depending on your fantasy, and that's a typical example of DEP bypass. So, that's it. If you have any questions, I'll be happy to answer. Or maybe at the end of the session. Thank you.